I don't think it's recording even now.
No, it has started.
Streaming has started.
Streaming has
I'm
started, not
sharing
recording.
the. No. Recording hasn't started. I'm sharing the streaming link on the group. Okay. You can find
Okay.
it on YouTube. Okay.
Okay.
So about week 9 and 10. So week 9 focuses on the EM algorithm and how we are implementing that on this problem. Right. So let's go through this. So main key concepts that you have to understand about week 9 is how we are. There are two steps in the EM algorithm, right? So one
Levin,
is
you'll have to be a little louder. Sorry. Still
okay,
can't hear
okay,
you.
okay. Is it better now?
Not much. Maybe it's my problem. I don't know. Preetham, can you hear Levin properly? Okay. Then please continue in that case.
Yeah. So the main thing is about the EM algorithm. So when do we need this EM algorithm is the question, right? Uh, so when we have this kind of latent variables, or which we call this mixture, here the mixture proportion is unknown to us. So that is what the latent variable here is. Right? So when we have latent variables, and but we want to fit over the marginal distribution, we don't know this P of Z or the P of X given set. We don't know the how this latent variables affects the distribution. So that's why we need EM algorithm for this case. Right. So EM algorithm is a more general case of the K-means algorithm. Like K-means is particularly for a certain structure that we use, and we saw different variants of K-means that we use, right? So EM algorithm is a more generalized version of what we saw. So going from the probabilistic view, so let me see how. Yeah. So here the main important part is we have the mixture component here, which is the latent variable, and uh, but given the data, we don't know which data point or the sample belong to which of the uh, latent variable. Right, assuming you randomly, so that is why this simple example of Bernoulli coins is given. So here we represent mixture components by using coins. So there are two coins, each having different properties or different probabilities of head and tails. And you randomly pick a coin and then toss the coin to get the samples from. So you have a collection of samples. You don't know when which coin has been picked, and uh, you don't know what is the uh, probability of getting a head with each coin. So you are collectively fitting a model in this case. So that is the EM algorithm, right? So first we study about the latent variables, and there's an example which is the Bernoulli mixture, which can be applied to any mixture distributions because uh, not only EM algorithm can be used for mixture models, but any latent variable models like there are different models like hidden Markov models, which are also latent variable models. So EM algorithm is a more generic version of for fitting this latent variable models. Okay. But we use here for using the mixture models. Yeah. So that is one thing. So here we know only the uh, yeah, we don't know this distribution, but we observe this only. So using that, how we are finding this latent variable part. That is, so this marginal is the observation. So using this, how we are observing getting the model. So first, there are two things. First we have to talk about inference. Like, given the parameters, how will you find the probabilities? That is one thing, or the responsibilities. That is the inference part. So since we won't be able to get this responsibility as the first, we randomly select these things. So all the parameters will be randomly assigned first. And with the model, we try to find the probabilities. So it's like the k-mean finding the nearest cluster path. So randomly assigning clusters and finding the nearest cluster path. Then using that, we find the responsibilities for each of these mixer components. Here we are particularly talking about mixer components. Right? So I think these things has been discussed in the previous weeks also. How you get the responsibilities for. Right. Yeah. Right. Yeah. So there are these two steps that we do. One is generation and inference, right? So we saw about generation. Then there is this inference. Generation and inference step. So this is what we want to maximize. Maximize the marginal distribution is what we want. So we want this. So yeah, so we cannot directly maximize the sum, right? So if so this is the sum over all the distributions. So this log and the sum don't go well together, right? So what we do is, yeah, we do this log across the sum, and we try to minimize, maximize this part, and then we do that. So that's how the EM algorithm works. So this thing is hard to optimize. So if you see in the optimization way of things, so it's like given we first take the random set of parameters next, and we maximize that one. And then after maximizing that, with that we find the new set of parameters and maximize for that parameters. That's how the overall likelihood that we have trained, we are trying to find that. So we assume the parameters and maximize the data, likelihood of the data, and then maximize the likelihood of the parameters, change the parameter, adjust the parameters so that it maximizes the likelihood, and this go back and forth until we get the optimal point around that. So that's the overall functioning of the EM method. So these are the two steps. One is finding the posterior probabilities and then doing the new ways. So those are the two steps. So this is a more generic question of the algorithms we have seen previously. And I think it will be better if we see the application. So here we take this mixture of anomalies. This is a generative model that we take. So it's like there are two coins. So we randomly pick a coin and toss the coin in number of times and note the number of tails and heads. So this is what we have. The number of tails and the number of heads that we receive is the data we have. This is we don't know which coin we picked or what is the probability of heads and tails in each coin. And then how do we fit this generative model? So must be randomly assumed this. So So there are 10 choices, process. Okay. So this is the probability of x equal to n given theta. Theta is the probability of theta is like here is theta 1 and theta 2, right? For 2 points. And theta 1 is like the probability of x in the first point. And this is like for the binomial probability we are multiplying with number of x minus total number of. So this is the probability of 2. So this gives us the posterior probability. So after finding the posterior probability, we are finding the responsibility for each of these clusters with the posterior probability of Z given A. So this also we are randomly assuming initially and then finding the responsibilities. So this theta is randomly assumed, and then we are finding this given this theta, what is the given this theta equal to 1, what is the responsibility for theta equal to 1? And we are so this is the two things. So this is like how do we fit if we know? So there are two things, right? If we know from which point or which point the sequence is generated, it is easy to fit. But if we don't know from which point the sample is generated, then we use the E method. So in this case, these are easy to find if we know the from which point the sample is generated, right? So otherwise, what you have to do is, yeah. So this is our this is the overall thing for the all the process product of all these things. Yeah. So then we are after finding the responsibilities. So this is when we know the data, we know the label, so we can assume the responsibilities to be 1 and 0. So if that coin was taken, the responsibility for that coin is 1 and that coin is on responsibility 0. And we use this formula to update the parameters. So this is we know the responsibilities. How are we doing this? Right. Then in this generic question, we don't know the, so this is like, yeah, so in the maximization, so what we do is, so without knowing, so there are these two steps, right? In maximization step, we assume that we know the responsibilities. So that is how we find the responsibilities and update the parameters. So first in the E step, we estimate the responsibilities. So given the responsibilities, we used to fit, right? So in the E step, we estimate which responsibilities, estimate the responsibilities, and in the M step, we estimate the parameters using the estimated responsibilities because we don't know the actual responsibilities. So that's how the M step proceeds. So this is like a flow diagram of what we do. So we have the data, we don't know. So we assume the parameters initially and the responsibilities. So with the assumption of these parameters, then we find the responsibilities. And then that is finding the responsibilities is the E step. Okay. And after the E step, then we update the parameters by using the responsibilities, assuming that. So if we know the responsibilities, we can easily fit the model. But if we don't know, we estimate the responsibilities, then update it, and then re-estimate the responsibility, and this cycle goes on. And that's how the works. And we do an application here for this motive finding problem, where this let's see how this problem is. So here here the binding probabilities, like the probability for a motif to bind at a particular location is given with the given profile, this factor, it's a table. So these are the parameters for this motif. So here, instead of having two coins, we have different positions. So what is the probability that a sequence having this particular thing is found? So we then use that table to find the probabilities. Those are the parameters. So we don't know which position this particular table is binding in. Here is include variable. Each position, what is the probability of a particular thing finding in this position? So basically, here what are the parameters? This problem is, this is the table for this motif. So these are the probabilities. Like all these values are what we are trying to find. So in the coin case, the coin p is kind of the Latin variable, and then the probabilities of the coin being that head or tail is one thing. Here instead of head or tail, we have 4 DNA nucleotides, and then this position will be the Latin variable, which coin is chosen. So similarly, it's a more complex version of that EM, right? A Latin variable model, slightly different from the conventional mixture model, right? But the concepts are same. So that's how we are using this EM algorithm here. So this given this profile. So we are trying to find this itself, the values in this whole table given the sequence. We have the sequences, and then we are trying to find this one. And you can see here, this is kind of instead of a Bernoulli, since here are 4 values, it will kind of become like a categorical distribution. That is what here, like a mixture of categorical distributions, you can assume it like that. Right? Yeah, so that's it. So you can see this one, right? So we are trying to find the probability of the sequence, right? From the given sequence, we are trying to estimate this profile, K1 profile, right? So from the sequence, we are placing it here, and when this is placed in this position, so this is like you know the position. So known which coin we are still estimating the responsibilities, right? Like we are putting it for each of the positions and finding the responsibilities. This is the E step in our algorithm here. So in the coin case, we know the which coin is chosen and we estimate the probabilities. And here we know we are assuming which for this position, what is the probability. Right? So with that we are finding the responsibilities, and that gives us with these probabilities. Then we do the M step, updating the actual table with that. So first we randomly assign these values, right? And then with assigned values, we find this these responsibilities. And then after finding these responsibilities, uh, yeah. So this is some observed sequence. Yeah. So if we don't know the location, then we calls for the EM algorithm. Yeah. So once we find the position, then how we update the parameters is by this. So here this is like a what is one action? It's like how we did the responsibility boundary. So known the sequence. So we after finding the responsibilities, we assume that the one with the most responsibilities has this right. So this is with the expected data for one. This represents if that position has more probability, we are making it that one, and the other position zero. It's like a categorical version of that. One part, like basically one part encoding is what this is. One part encoding of the positions and the responsibilities for the positions. And that we will be doing EM algorithm to find this motive thinking from the PAM of this profile, we will be able to find. So considering all parameters. So it's like a very kind of enlarged version of this Bernoulli mixture problem. Okay. So without still now with this one. So in week
So
10,
here in this in week 9, the focus should be more on the theory part, or is it more on the application, the numericals, etc.? Because when I try to go through it, a lot of the questions, I mean, I'm not talking from an exam perspective, just generally trying to understand. A lot of the questions are mostly on statistics. The questions are not really on bioinformatics in week 9, as far as I could see.
so that the reason for that is because, so if you see, if you are asking a numerical question from motive finding problem, the number of parameters are known, right? So
Yeah.
estimating that would be, asking you to estimate that would be very, there's some foreign example. So we'll have a similar problems to, similar to this example problem, since this is also not related to bioinformatics in some sense, right? So the focus is on EM algorithm in that case.
So then, how do we test our understanding of this chapter?
So most of this chapter is about understanding the EM algorithm, right?
Okay, so we should not focus on the bioinformatics, only on the EM algorithm. That's the main part.
It's not, I'm saying that you shouldn't focus on the bioinformatics part. From the bioinformatics part, asking numericals will be difficult. So there may be theory.
No. I'm sorry, Levin. Maybe I can just clarify. I'm saying that generally, so let's keep the exam and all those things aside for the time being. If I want to so there are in the previous weeks, there are a number of questions. When you try to solve the questions, unless you know the concepts, you cannot solve them, right? You cannot just start doing something randomly and solve them. So is there any so should we refer to the textbook to see questions around this? How should we test our understanding of this topic?
So actually, this week 7, 9, and 10 are more focused on using ML algorithms to solve bioinformatics problems, right? So those weeks are more focused on the ML concepts. So it's not that. So it gives you an idea of like certain problems in bioinformatics can be solved using ML, right?
Okay,
So,
got it.
that's the idea of this thing. So you might not have thought about can we do this one using EM algorithm kind of thing, right?
Okay. Okay, understood.
So
So the
our
application part is the most important part to understand from a bioinformatics perspective. That
yes,
there are problems
it's
in bioinformatics that can be solved relatively better by using EM algorithm.
yeah.
Okay.
So if you see here also, most of this week 10 is about so given a usual DL problem, so a common DL problem, how will you
Right.
do the things? So here in this unit, it's about the architecture specifically for this bioinformatics. For example, assume you have image data set. You know how you can design a deep learning neural network to process, classify the images, right?
Right.
So the concepts from deep learning is there, but how we tailor the model or extract the features related to solve a problem in bioinformatics is what we are seeing. So we are taking a case of an existing model, which we call DeepMind, and see the architecture, how the data is processed, how we are setting up the parameters, how we are framing the problem is the important part of it.
Got it.
And let's move on to this one. So here, so we did something using the CM algorithm, right? The same thing we are kind of trying to find using a deep learning solution. So the motive finding problem is all it using this EM algorithm, right? But can we do a more sophisticated way for finding this? Okay? So that's where this deep learning solution comes from. So here, so the important parts of this is like, okay, let's see. Ah, yes. So here we are trying to find there are different paradigms of model, right? This yeah. So this motive profile. So this is something that we are trying to estimate, right, using the EM algorithm. So instead of estimating it using a probabilistical method, can we estimate? You can assume this thing as a convolutional kernel, right? So can we process the strings as you do in the sequence, 1D convolution in sequence, right? So there are certain ways in which you can do 1D convolutions uh, and in text data also. So similarly, so here the idea is since this matrix looks like a kernel, can we try to find multiple kernels instead of just finding one kind of motive? Can we find multiple kernels by using it in a deep learning model as with convolutions? So here we will be using convolutional network only. So whatever we are computing here is basically kind of like a, so this process, you can see the similarity between this thing and the striding that you use in 1D convolutions. So in 1D convolutions, you just move the kernel in one direction, right? So we use that kind of method to estimate this kernel values. So in a deep learning model, what you will estimate? Convolutional, you will find the convolutional kernel weights, right? So here this PWM is also like a kernel. And with the data, we will be finding the uh, values. So that is the main idea about this. Okay? And let's see the model architecture and training process and how we are using. Yes. basically, how we are training this is now we want to find whether this sequence, the motif will bind or not. Right? That is one thing. And then we have the current set of input sequence. So how we are training this? Here, this motif scans or the PWMs, or here we call them as motif detector. I think in convolutional setup for images, people are call that like feature extractors or something like that, right? So in the same sense, so this gives you a sense of how you can process the bioinformatics data with neural networks with certain assumptions. So that is the idea. So in our training data, like if in our training data, it can be the binding score. This prediction value can be either a binding score given the sequence, either a binding score or a whether it is will bind or not, 0 or something like that. So it can be binary or we can decide on the error function based on that. If it is a score, we go for regression. If it is a binary data, we go for classification. So it's like a basic convolutional layer at first, and then there is a rectifying and pooling layer, which is basically like rectification function after the convolution. Rectification is like the kind of different form of the loop, and then there is this pooling layer. Then these after pooling, these features are flattened and then used an ANN like fully connected network is used to give us the output image. That is basically the overall structure of the deep mind architecture. Parts. So this is the whole thing, MS function. So this is an evolution and then rectification, pooling, and then neural network. This can be. So there, one more thing. There was a slight confusion about this rectification formula right here, because these two definitions are quite different in its own. So what this is saying is, if it is greater than B, it is V, else 0, which means it would look like a cutoff layer. But ReLU of V minus B is like a shifted.
Can you, is it possible for you to just draw this and show it?
Let me check.
I mean, it's okay if you want to just post it later, that's also okay. I'm also confused on this one actually.
I think it will show it here. So this function, V greater than V, is a equal to by square root of U. So if x is greater than p, then it is x. Else 0 is the first thing that is given. So you see here, it would look like it would look like a line that is cut off at some point. Right? You see that this is the one that is being described here. What is written here is the ReLU of A minus B. So ReLU of A minus B is by definition will come like this. X
Shifted.
Shifted what, right? So it is like ReLU of x A minus B will be like x minus B if x minus B greater than 0, then x else 0. This is the same then.
Maybe you can use a different color.
I think both are we using the ReLU? Okay.
You can change the value of B and C. You can make it B 7 or 8 or 10 or something like that. It's just shifting down.
I think I did something wrong. Oh, x minus b. Research implement ReLU. Will be like x if x greater than 0 is 0. So this one looks like the ReLU function.
Got it. So that triangle is getting clipped out.
This problem. This is the
Yeah.
ReLU function, right? ReLU
Yeah,
of something ReLU of A minus B. So if we are using ReLU of A minus B, both of these B's should be getting what I guess this assumption is the shifting assumption is. Here it just change this expression, keeping the other part same, right?
got it.
So if we do L4 equal to L3 of x minus b. If you do something like this, then you see these two things will happen. So this is like a shifted ReLU. See this one? L4.
Yeah.
It will be like a shifted ReLU. But what is given here is kind of a clipped out ReLU. Like if this is less than
Not just clipped
zero.
out, right? It's also shifting. Now I understand better.
So this version, the original version, this version, you see, you can think it of like these values are being turned out to zero instead of being here. It's not like we are shifting it, right? But this one we are shifting it like this. See this?
Yeah,
Both values
got it.
shifted.
Yeah, so that is moving right by 6
Ah.
units.
So I
And
have
this one is
yeah. which definition does ReLU of x minus b sir might have meant? Sir might have meant this interpretation where you
Right.
just change the value like that.
Got it. Oh, now I understand much better. Thank you.
Now, let's see. This is about the loss function. So there are two regression and classification tasks are there. So we just use the MSC and the weak splitter and then negative log likelihood, which is the cross into the loss function. It's for the loss function. And then there is also, they are using this ridge regression or what you call like L2 normal, L2 regularization. Right? This is we are adding a constraint on the weights also using this L2 norm. So that is we call L2 regularization or ridge regression setup using the loss function. Then we do the gradient descent or different deep learning optimization techniques we can use. So these are the general topics which are key. You might have known, right? The back propagation and other stuff. Then there is about the hyperparameter tuning process. So they have a data set. So how do you find out the set of parameters? So they did here they did a threefold cross validation process. Threefold cross validation is like to split the data set into 3 parts, keeping n minus like you a-fold validation is a general case where you split the data set into 3 parts and use the k-1 part for validation and like keeping 1 part aside, keeping k-1 as training and 1 as validation, and doing the same for different keeping different part as a validation data set. And then you do the average of like finding the like this is to establish the find the good set of parameters. That is one thing. Then after like first do the different parameters with different hyperparameters, and then do this training with different parameters, and then do the evaluation using the threefold cross validation to find the best set of parameters. Then finally you have a test data set on which you put the test accuracy. This test data set is not used in either validation or the training. That is the concepts are very pretty similar to the ones we have learned in the. This is kind of but you can see the alignment of how what kind of things or what kind of parameters that they are feeding in this network. Those kind of the additional information is what you are learning from this example. And this is about how we are using this DeepBind results, testing them on this binding sequence. So this is like the evaluation of how DeepBind has performed in comparison with the previous models is what the DeepBind reports are. So these are basically the findings. So basically, this unit is analyzing a particular paper. Is what you can consider. what are we interpreting from the learned motives. So these are like the kernels that we found, right? So is there any interpretation for that, or is there any significance for that? So what that we found is like most of the learned things are very similar to this. So this learned motive predictors kind of maps with the already existing motive that we already know from the tests. So this is something that interesting that we found using the deep learning models. This is basically the results and findings of that. Then there is this another interpretation of how this location. So this is like how we identify, like with the defined interpretation, how we identify the mutation in a certain genetic sequence. How does the mutation affects? So, for example, we know the binding score for a particular sequence, and then mutating binding score is something out of the model that you can say. And then there is this score for the mutated sequence, and how the difference affect the. So, what can we interpret about the difference or the effects of the mutation in that particular sequence? Is what we can do using deep. So this is how we can use the deep brain model to find something like this interpretation. So does this mutation cause any difference in the binding characteristics of the sequence? Is what the question is. So we run this through the sequential sequence and the mutation sequence to the deep brain model to get the score. And with the score, we are finding this delta. This delta, like basically the difference, but also multiplied with the maximum of these three things. So, for example, assume this sequence doesn't bind, so the binding score is 0, then we don't care much about what this is. So, like, for example, if both of this are not binding with the particular thing, then we won't be able to know much information about the mutation from this model, right? But assume, so that's why this max is there. Assume this probability, these two probabilities are very low, then this difference doesn't make more sense. That is what we are weighting the difference using the maximum of this thing. But one of these, like for example, if these particular sequence has a very high probability and this mutated sequence has a very low probability, like we don't care about it. Just as if this one has more probability, and then whatever this is, then we weight the whole thing, the difference, using the maximum. So that is what the significance of this max is. Both are low, then we doesn't weight the difference much. If one of them is high, we weight it with the highest probability. Even if this probability is low and this probability is high, then we will have a higher significance. Is what we are trying to find the effect of. So that is basically this example showing that if one difference is 9, this difference will scale up a bit much more. But assume here the difference is okay. So let's see. If this one is 0.9 and this one is 0.89. So the difference is 0.1. But since this maximum value is high, you will get a higher score, higher significant score. But assume both of these are shifted, and this is 0.1 and this is 0.09. Then the whole this max component will reduce, right? So that is something we that's about the interpretation of how this how we can use the guiding score for the deep brain model to identify the effects of the mutations. That's so many doubts.
Well, this one was okay. I mean, I don't know what Preetham, but for me it was fine.
Yeah,
Yes, sir. It is fine. I understood.
okay. Okay, then. Okay. Then you can stop this. Thanks for joining. Yeah, so we can start the recording.
Thank you. Thank you so much.
Thank you, sir. Thank you, ma'am.
Livin.
Yeah.